Have you ever tried to learn a new board game or maybe a sport when nobody gives you the instructions? You just have to jump in, try stuff, and figure it out as you go? Well, today we're going to dive into how modern AI tackles that exact same problem, learning how to win with nothing but trial and error. So, here's how we're going to break it all down. First, we'll get a handle on the problem itself. Then, we'll meet two totally different AI learners. We're going to put them head to head to see what makes them tick. And finally, we'll figure out how to get the absolute best of both worlds. You see, for an AI, the real challenge isn't about just reading a manual someone wrote for it. It's all about learning directly from raw experience. It's the digital version of just trying things until something clicks. I mean, really think about that for a second. How do you do it? This is the absolute core of the challenge. In the AI world, they call this model-free reinforcement learning. And model-free is just a fancy way of saying you don't have the model. You don't have the rulebook. All you've got is the game itself. So this really splits things into two big camps. On one side, you've got model-based learning. That's where the AI is like a grandmaster with the entire rulebook memorized. But we're not talking about that today. We're jumping into the deep end, the model-free world, where the AI is basically an explorer, drawing the map as it ventures into the unknown. All right, so let's meet our first contestant, if you will. We're going to call this one the patient observer. Its official name is the Monte Carlo method, and believe me, it is meticulous, it is thorough, and it's in absolutely no rush. You know, the way it works is actually super simple. The AI plays one whole game, what researchers call an episode, from the very beginning to the very end. It waits to see the final score. Only then does it look back at everything it did and say, okay, all those moves together led to a win, and it gives a tiny bit of credit to every single decision it made along that path. Okay, that's the theory, but let's make it real. And there's no better place to do that than with a classic game like Blackjack. The goal's simple, get to 21, but the right strategy, well, that's a whole other story. Okay, so check this out. This is how an AI sees the game. It doesn't see cool-looking cards, it just sees data. To the AI, any situation in Blackjack is just a state, defined by these three numbers. What's your total? What's the dealer showing? And do you have an ace you can play high or low? That's it. That's its entire universe. And this quote from AI researcher David Silver just hits the nail on the head. The AI isn't doing some crazy math in its head, calculating probabilities. Nope. It's just playing hands, millions and millions of hands. And every time it's in a state, like having a 17 when the dealer shows a 7, it just keeps track of whether it won or lost and averages it all out. It learns what a situation is worth through pure brute force experience. Okay, now for something completely different. Let's meet our second learner, the impatient guesser. You might also know it as temporal difference learning, or TD learning for short. This one is fast, it's nimble, and it absolutely refuses to wait until the end of the game to learn something. The secret sauce here is this really cool idea called bootstrapping. It sounds technical, but it's not. All it means is you update a guess based on, well, a newer, slightly better guess. You don't wait for the final answer. You learn from your own constantly improving predictions. Let's put this in real-world terms we can all understand. Picture your morning commute. You step out the door, take a quick look at the traffic on your phone, and you make a guess. Looks like 30 minutes today. Now, our patient observer, the Monte Carlo method, would wait until you're parked at your desk 43 minutes later, and only then would it say, okay, that 30-minute guess was wrong. But TD learning? No way. It's live updating. 5 minutes in, it starts raining. Uh-oh, your brain immediately updates its guess to 40 minutes. Then, 20 minutes in, you hit the highway and it's wide open. Great, you revise your prediction down to 35. See, it's learning and correcting at every single step. Okay, so we've got our two contenders, the patient observer and the impatient guesser. So which one's better? Well, like with most interesting questions, the answer is it's a story of trade-offs. Let's put them in the ring. This table really lays it all out. Monte Carlo waits for the real, final outcome, so its information is totally unbiased. But that also means it has high variance. A single, ridiculously lucky game can make a terrible strategy look like a brilliant one for a little while. On the other hand, TB learning is technically biased because, well, it's using a guess to update another guess. But its variance is super low. The updates are small and steady, so you don't get those wild swings. So what does all of that bias and variance stuff actually mean in practice? It means that TD learning, because of its low variance, is just way, way more efficient. It gets to the right answer with a lot less data and a lot faster. And in the world of AI, efficiency is king. Learning faster means saving enormous amounts of time and computational power. And here's the real kicker, the big aha moment. TD is so much more efficient because it gets the structure of the problem. It understands that this state leads to that state, which leads to the next. Monte Carlo, on the other hand, just sees a big jumble of moves and a final score at the end. It completely misses those step-by-step connections. So, after all that, which one should we pick? The patient one or the speedy one? It turns out that's the wrong question. The most powerful AIs don't have to choose. They find the sweet spot right in between. Think of it like a slider or a dial. All the way on one side, you have pure TD learning, updating after just one step. All the way on the other side, you've got pure Monte Carlo, waiting for the whole shebang. But what about updating after 2 steps or 10 steps? You can actually pick any point along this entire spectrum. This is where it gets really clever. An algorithm called TD Lambda comes in and basically says, why choose just one? It brilliantly combines all of them. It takes a weighted average of the 1-step update, the 2-step update, the 3-step update, all the way to the end, giving a bit more importance to what's about to happen soon. So at the end of the day, the smartest way to learn isn't to be purely patient or purely impatient. It's to be flexible. By blending these two powerful ideas, an AI can get the best of both worlds, the raw accuracy of the patient observer and the lightning speed of the impatient guesser. And that really brings us to the final big idea. If an AI can teach itself to master a complex game like blackjack, or even something as vast as Go with absolutely no instructions, what else can it learn just by doing? From discovering new drugs to designing more efficient supply chains, the possibilities of learning without a rulebook are really just beginning to open up. Thanks for joining me.